Alright, so today we're going to be looking at the debate of light. So is it a wave or particle? That's going to be looking at the works of Isaac Newton and his contemporary, or actually senior, in Christian Huygens. Before we start, I just want to go through this nice little do now question. And it's saying you have 3 stars, and the question is which one is the fastest, so in terms of velocity, which one's the fastest, which one's the slowest. Okay, now we remember from the Doppler effect or the absorption spectra, if it is a redshift, so lines are going towards the left, it's moving further away from us, so it's also the fastest. So star number 3 would have the greatest redshift, and so it would have the fastest movement away from us. And then we have star 2, and then we have star 1. As you can see, in star 2, although there is a bigger shift towards this point here, so this point that we see here, alright, it doesn't really show us as big a change as, let's say, this point here. Okay, we can see that on this particular point, in the 500 nanometers, there's a bigger shift away from the blue, hence it's moving the fastest in that particular direction there. Okay, so moving on. Okay, whoops. Alright, so our journey today will be exploring Newton and Huygens' model of light, and then we're going to look at some experimental evidence that might inform us of whose is more valid, at least for that particular point in time. Alright, so in this investigation, or for this particular dot point, just change it to a laser pointer. In this particular dot point, we are being asked to analyze the experimental evidence that supports the model of light as proposed by Newton and Huygens. So back in the early 1600s, there was a big debate: is light a particle or is light a wave? Right now we actually know that light behaves as a particle and a wave, so what we call wave-particle duality, but at the time we tend to sort of separate the two concepts away from each other. If we look at the general overall history, we start with Democritus. So this is the guy who also came up with the idea that atoms, the concept of atoms, particles are indivisible components. He also thought that light would be a particle at the time. That was in 400 BC. We had Ptolemy, so one of the people who talked about the heliocentric model of all the planets. He said that light illuminated from the eye. So we would have particular senses from our eyes that go out and touch and sense the physical world, and that's how we were able to see things. So that's why when our eyes look into bright objects, it would damage us, because the concept was that your eye, things from your eye would go out, and if it was, say, to the sun, it burns that, so the actual transfer that helped you see the things is being broken. That's how you cause eye damage. That's his concept or conceptual understanding. Then we have this gentleman here from the Middle East, and he believed that light behaved like a particle because it could be reflected and refracted, which, if you think about it, it's really an easy concept to explain if you're thinking about particles. If you're throwing a book or you're throwing a rock onto the wall, it just kind of bounces off the surface. And so that's, if light does things like that, and we can throw a rock which is just a particle or like a particle of mass, then it kind of simultaneously works similar to how we see the physical world. So it made sense at the time. So the question we're looking at here is what experimental evidence supported the model of Newton, so this guy here, and what model supported this guy here in Christian Huygens. Now Huygens, to give you a bit of context history, is about 20 years older than Isaac Newton. But Newton was a lot more well known, so he had a much bigger reputation because of his work with gravity. So, much more well known, the senior priority here. Okay, let's just quickly have a quick overview of what they actually said. So, Newton had this concept of the corpuscle theory, so light behaving like corpuscle particles. Light will always travel in a straight line until they hit a surface. It doesn't explain, his concept does not explain diffraction or interference. Okay? Huygens' wave model says that light can behave like a wave. At every point, the wavefront is a source for a small wavelet, creating a new wavefront. So we're going to look at what that actually kind of means. The key point here, and there's another key point, is the wave model explains diffraction and interference really nicely. The particle theory doesn't really give you a nice simple explanation of how diffraction and interference works. However, in the 17th century, so in the 1600s, that's what we mean by 17th century, okay, Newton's idea was more accepted at the time, purely because he was the more reputable scientist, and there was no real experiments to demonstrate diffraction and interference at the time. Alright, so let's just kind of look through this. So light, this is Newton's theory of corpuscles. Light consists of tiny little particles, he called corpuscles, and they had mass. Okay, the basic principles, it's a small particle. These particles have mass, and so they behave to the particular laws of physics. So it is subjected to gravity. Okay, so gravity will pull things in. The understanding at the time was that gravity would act on objects of mass. So that's the idea there. The particles are so small that when two beams cross over, they do not scatter each other. Hence why you have sharp shadows. Okay, so they're so small, they won't bounce into each other, so a light particle won't kind of go through another light particle, hence you have a really sharp shadow there. If we're looking at the work of Christian Huygens, he's building on the work of Robert Hooke. Said it many times in any other videos. Robert Hooke was a scientist that had a real big beef with Isaac Newton. So any images that you see of him, even including the one we have here, is not the actual portrait that we know of the time. It disappeared when Newton became the new, director of the Royal Society of Science in England. Christian Huygens is building off the work of that. So let's kind of look at what his idea is. Okay, so according to Huygens, waves create wavefronts. So these kind of lines that we have here. Okay, and in order for this wave to move, okay, in order for a wave to move, it creates little source points, or point sources. So every time a wave moves, that particular wavefront, there's going to be a little dot that is where the actual wavelet forms from it. So the wavelet will travel out this way from the center point, out this way from this center point, and it keeps building on each other. Okay, and so they kind of spread it in all directions. If you add, or his idea is, if you add all those wavelets together, the tangent point of all the wavelets, this forms a new wave front. That's the idea of how waves traveled in Christian Huygens' mind. Okay, so each point behaves like a wavelet. You can see the little point here goes out, starts here again, goes out, and keeps going. Goes out, keeps going, and keeps building on to that. If you were to find the tangent points of all those, you can kind of just draw it out and make the line like so. Okay, so let's look at their different observations and see what they said about each one. Firstly, we're going to look at refraction and reflection. So for reflection, Newton's idea was very simple. You have the ray of light, or the particle of light, coming in. That's called the angle of incidence. That angle to the normal line is the same as the angle of reflection as it bounces off. Huygens one is a little bit more creative, and let's kind of look at that here. So we have our wavefront, these two lines here. I'll change the color. We have these two lines here coming down like that, and you have your wave front. So the wave is going in this direction down. As it comes down, one side will hit the point first. The other wave front takes a little longer to catch up. When this point hits, when one point of that wave hits, it's going to create a point source, and it's going to create its own wavelet. As it creates its first wavelet, it's going to continue to move out until this side of the wavefront hits and creates its own wavelet and goes out like that. When they've both been created, or when they both are deflected or reflected, you get a new wavefront going in this direction out that way, so in that direction. Okay, so hits the mirror, creates a circular wavelet, and then they're both reflected out. Exactly the same idea. The angle of incidence is equal to the angle of reflection. So you can see from that, Newton's particle model of reflection kind of explains it a bit nicer, a bit more simpler. The wave model, you know, is a little bit more complex. Okay, so new wavelets associated with their wavefronts, leaving at the angle of reflection. Remember, both of these are saying that you still get the same angle of incidence to the angle of reflection regardless. With Newton's reflection model, he also stated that to the normal line we have here, there is a force of repulsion from the surface. So on the surface, there's a repulsive force which will slow the light down. So as light comes down here, its velocity gets smaller and smaller and smaller until the force reverses the direction, and it will get faster and faster back out that way. So let's try and summarize what they kind of said. Newton said that light is repelled by the surface force. Huygens basically said each wavefront that collides with the surface produces a new wavelet, hence that's why it's reflected back the opposite direction. Newton said the normal component of the light is reversed, or its speed is reversed, so it's moving in a different direction, and decrease. So as it gets closer to the surface, its velocity will go down, and then it gets repelled, and then it goes back up. Huygens basically said the new wavelet overlaps each other and travel away. So he didn't have any new explanation about the speed of light. He just said it gets reflected by producing new wavefronts. Both agreed though that the reflected angle would equal the approaching angle, or as we call it, the incident angle. Okay, we have a little diagram of the lady with the mirror. Let's just go through quickly. This property is showing reflection. Reflection is just bouncing back of waves. Particle model proposed that it would simply jolt the surface and bounce back. And the wave model says once it hits the surface, point impact acts as our point source to create new wavelets, hence bouncing out and propagating in another direction. The next one we're looking at is refraction. So, just to start off, Newton basically said if a particle, or if light, because it's acting as a particle, the reason why it doesn't refract in its own medium, in this case let's call this medium air, the reason why it doesn't get pulled in any particular direction is because it's being pulled in all directions. So if it's being pulled in all directions, the net force on this particle equals to 0. So it can't be pulled in any other directions, that's why it doesn't refract. If it reaches a surface, or close to a surface, that interphase, so as it's approaching, the forces from that newer surface, the denser surface, let's call this water, let's say it's water, that is just creating an attraction force that's pulling the particle down. So pulling it in its normal component, in this case the normal component is also the y component here. And so he came up with the idea that when light approaches a denser medium, okay, the net force is pulling it towards the normal of the surface. So if this is my normal line, the force is pulling this thing down, hence why it bends through the line. Now his idea was the tangential velocity, so this tangent velocity here, that is the same. Okay, that hasn't changed regardless. What he did say though was the velocity going down in this direction, the normal component, that velocity has increased. And that becomes a point of contention, as we now know when light goes from a less dense object to a more dense object, it gets slower because it's interacting with more of the particles. Newton said it increased if that was to happen because of this idea of the force pulling it down. Okay, what about Huygens? What did he say? Well, very similar to what we said before about the new wavelets. We have our wavefront coming down like so. One side will always get there before the other. When one side hits it first, it's going to propagate the wavelets in all directions. When the other side finally reaches, it's also going to propagate the wavelets in all directions. Now because one side reached the surface first, the wavefront will start on that side first and then followed by the other side. So that's the kind of explanation of why it's bending there. Okay, so there's that. Now Huygens, I don't think I mentioned it here, or I did mention it in the next one, but Huygens mentioned that the velocity here compared to the velocity here, let's call that the velocity there of air and the velocity of water, he said this one here, the velocity in the water, is slower than the velocity in air. Okay, and that's the idea of how waves behave, right? It will interact, and because it's interacting with other things, it will have to slow down. So let's compare again. By approaching a denser medium, the particles will experience an attractive force. We see increase in the normal component's velocity. Okay, fills in empty space. Huygens' description is if it meets a heavier medium or denser medium, the wavelets do not travel as fast, causing a change in direction. So his end conclusion, we have one that says the wave will slow down in a more dense medium, and then we have another one that says the speed will increase if it's in a denser medium. Both agreed, following Snell's law, of how things bend. So there's that there. Okay, the next one we have is diffraction and interference. Now, a quick recap of what diffraction is. Okay, diffraction is defined as an obstacle that will block the passage of a wave. Okay, or the grating. So a wave can come here. You can call this where our point source is. Now, diffraction, what happens with waves is, or according to Huygens' explanation of it, the wave will come close to it and then it will break away. Right, so it will move around the obstacle or bend around it. Okay, and so that kind of shows where it spreads in all different directions as it creates new wavelets, and that creates a new point source for the waves to kind of move in all directions. If you then look at it, you add the tangents all together, it'll look like it's moving straight ahead, straight through like that. Okay? The only issue with this is this explanation wasn't accepted at the time because they couldn't prove it. There was no scientific evidence at the time, or at least there wasn't enough evidence shown to do that particular experiment. Okay. Another thing we also know is if you have a double slit or you have any diffraction, you get this interference pattern here. Now, if you recall, if you get a bright band, that is showing constructive interference. So the waves are meeting at the same maximum. So like that. If you get destructive interference, the waves are meeting at an opposite orientation to each other. Now, the thing that's really strange is if you do diffraction patterns, you'll see that the center band is the brightest part of the whole thing. But you have a little obstacle here, right? So if light was a particle, why is there a center band here? Why is there a center bright band here? Because if it's a particle, it should just go straight through. Let's change the color. If it's a particle, it should just go straight through. And then you'll get your bright band here, you get your bright band here, and then everything else should be dark because particles can't move around, a barrier. Waves can, particles can't. So what that means is Newton couldn't actually explain diffraction or interference very well because that wouldn't really fall under anything that we know of that particles do. His way of explaining it is that the light particles would create a localized wave in the ether. Now, you don't really need to know what the ether is at this point, okay? Just a little medium that they thought where waves were. But he thought that these particles would create a wave. Now, if you think about it, if you need to borrow a different model to help your model to explain it, you're probably not on the right track here. But he had the bigger reputation, and there wasn't really much evidence of interference and diffraction experiments at the time to build upon. So the particle theory was the dominant theory of thinking at the time. So this is in the late 1600s. It took another 150 so years until they actually showed the wave model of light by the name of this man, Thomas Young. So Thomas Young did his famous double slit experiment. So interference patterns, you can see here a famous experiment that was done by Thomas Young. And he showed that there is this center bright band and then these ones here. Okay? And then you had these destructive interference lines. So that was thanks to his work here. You had another man, Foucault's mechanism. If you remember what he did, he showed the speed of light. So his way of measuring speed of light, just for those who forgot, is you shine the light source in a rotating mirror that deflects it through a tube, hits another mirror, light comes back and reflects towards you. Now, if you know the speed of light, you should be able to work out the angle. So if you recall, what we were looking at was angular velocity equals the change in angular displacement over change in time. Okay, and if you know the distance it takes for this particular light to travel, and the time it took for it to bounce back to the detector, you should be able to work out the speed of light, because you should know how fast the mirror is rotating there. Now, if speed of light was to be slower in a more dense medium, the angular displacement here would be larger here, or it would rotate for a longer period of time. So what they found was the overall change in angle, the time it took for the light source to go through a tube of water in comparison to a tube of just pure air, it took a longer time. So time was longer when it went through a tube of water. So what that proved was light travels slower. So light, it travels slower in a dense medium. So what's that proving to us? That's proving Huygens' explanation of refraction of light. Thomas Young explained or experimentally showed interference and showed how waves behave. So that's very important. Other things that we can see, and you can try it out yourself, is if you put your hand over the tabletop and you have a light source above, you'll see that your shadow doesn't give you a very sharp edge. What's actually happening is you get very blurry shadows. Alright? If you look even closer, you'll find that your shadow will have areas where it starts off with a really dark band, and then it gets lighter, and then it gets brighter again. So what's actually happening on the edge of your shadow, your hand is actually causing diffraction of light. That diffraction of light is also causing an interference pattern showing as you look at the shadow there. If light behaved like a particle, you should get really sharp shadows. You should almost get a perfect shape around your hand, like if you were doing spray painting. But you don't see that. You see blurry shadows. You can only explain that if light was to diffract and interfere with each other. We have the Poisson's spot. So the idea is if you have a shadow of a circular disc that does not have anything in its center, still manages to produce a bright spot in the center of the shadow. If light behaved like a wave, like we said before, you shouldn't see that. It should be completely dark. Another thing that you can see, like I said with the shadows, you can see it's a bit dark here, it gets brighter here, and then it gets dark here, and then it gets brighter here, and then it gets darker here. Now it could be just the image I used, but you can see that our concept of interference, you have our destructive interference here, you have our constructive, destructive, constructive, destructive. So you can see there's an interference around the shadow that we have here. So that's kind of the explanations of it. Young basically showed the particle theory could not show how light bends around corners. It supported our wave model of light. The speed of light experiment showed that light traveled slower in water than air. So it showed that light was deflected when traveling through water, and it also supported the wave model. Shouldn't be supposed, should be supported. Okay, and so this is what I was saying here. If light did behave like a particle, this is the only bright bands we see, not the ones that we see in the interference patterns. So there is that. And what we also know is if it's a diffraction, the center point gets the bulk of the intensity, and then it gets accumulated on the other side as well. Okay, so supports our wave model and such and such. Alright, so that ends this particular lesson. That's just a nice little summary of what's to do. If you're looking into other components of the Module 7, so this is Module 7 Inquiry Question 2. If you're looking into other contents related to this, there will be a link up in the screen here, so you can look at it anytime. There are some also nice videos of other modules that are on this site as well, so please make sure use some time, really try and understand the debate with Newton and Huygens. And ultimately what we do know, at that particular point in time in the 1800s, the person who was most correct was Christian Huygens.